Hello, and welcome to this video on an integral of a rational function. So here our rational function is a quadratic over a cubic polynomial, and the cubic polynomial is already decomposed into two factors. We have x and then a quadratic that cannot be reduced because its discriminant is strictly negative. So when we look at the discriminant of the quadratic, we find b squared, so that's 2 squared minus 4 times 1 times 2, and that's 4 minus 8. That's definitely negative, so the quadratic cannot be decomposed into linear factors with real roots. To work with this problem, we want to set the integrand, the function we're integrating, equal to a sum of fractions that look simpler, that are easy to integrate. And because we already have the decomposition of the denominator, we can tell that factors induce the following decomposition. We have a constant divided by x plus a constant times x plus another constant divided by the quadratic. So now we need to find a, b, and c so that this is true in order to get to find the integral of our function in terms of easier integrals. So we're looking for x squared minus 3x plus 4 over this term. That has to be equal to, and on the right-hand side, we have x times x squared plus 2x plus 2 on the bottom, and then on top we have a times the quadratic, and then plus bx plus c times x. So we find that we want numerators to match. X squared minus 3x plus 4 has to be equal to a times x squared plus 2x plus 2, and then plus bx plus c times x. All right, now to find a, b, and c, we can do many things. We can, for instance, let's see, we can say that x squared minus 3x plus 4 has to be equal to, and here we have a times x squared, and then b times x squared, so a plus b times x squared, and then terms with x will be a times 2 and c, so twice a plus c times x, and then the constant term will be 2a. And as we match coefficients, we see that a plus b has to be 1, 2a plus c has to be -3, and 2a has to be +4. And there we have a system of 3 equations with 3 unknowns. We can solve that system by using substitution. Notice that from the third equation, we get that a equals 2. And then as we substitute 2, we get twice 2 plus c is -3. So c is -7. And then from 2 plus b equals 1, we get that b is -1. So x squared minus 3x plus 4 over x times x squared plus 2x plus 2 is the same as 2 divided by x. Then b is -1 and c is -7, so we can write negative, or just write plus, and then minus x minus 7 and then divided by x squared plus 2x plus 2. And because we have a negative sign both in front of x and in front of 7, then we can always factor out that -1 and then write this as minus and then x plus 7 over the quadratic. Okay. So now that we have the decomposition of the term, the function we were given, the integrand, in terms of fractions, let's see how we can generate integrals that are easy to work with. Let me copy and paste. We'll take a screenshot of this part as we move forward. Okay. Okay. Now, integral was 4. Let me just double check here. We have this one. Okay. Notice that when we integrate this side, this would be the integral of this minus the integral of that. The integral of 2 over x is twice the ln of the absolute value of x, so that part is really easy to find. The one that doesn't look as easy is the integral of x plus 7 over the quadratic. In order to use substitution and take this as u, we will need du to show up somehow on top. And du is twice x plus 2. And on top we have x plus 7. If we had an x plus 1 instead, then the top part would be really similar to du divided by 2. So let's decompose that x plus 7 as x plus 1 and then plus 6. That way we end up with x plus 1 over the quadratic and then plus 6 times -1, so that's -6 over the quadratic. Okay. Then when we do that, what we find is that the integral of the function we were given x and then x squared plus 2x plus 2 with respect to x is the integral of twice 1 over x minus the integral of x plus 1 over x squared plus 2x plus 2 and then dx minus the integral of 6 over, and I'm going to rewrite this quadratic as x plus 1 squared and then plus 1. And now we can solve those integrals very easily to find twice ln of absolute value of x minus, as we were saying before, excuse me, we had a du over 2 on top, and then we have a u on the bottom, and then minus, and this integral actually gives us a tangent, an arctangent of x plus 1 as we use substitution. So we have twice the ln of x in absolute value minus a half of the ln of u, and u is x squared plus 2x plus 2. In absolute value, that's actually going to be positive. And then minus 6 times inverse tangent of x plus 1 plus a constant c. We're going to add k instead of c so that we don't call two different things c. Okay, so here we have the ln of absolute value of x squared, that's the same as x squared, minus the ln of the square root of x squared plus 2x plus 2. That quadratic is always positive, so we can always remove that absolute value. And then minus 6 times the inverse tangent, or arctan, of x plus 1. So we have the ln of x squared over the root of x squared plus 2x plus 2. And then minus 6 times inverse tangent of x plus 1 plus an integration constant. And that's the final answer. All right. If you have questions, let me know. I will be happy to help you. Bye-bye.